Welcome to ATMOS 5000, day number 35. We're focusing in on Stull, Chapter 10, sections 10.6 and 10.7. We'll review the horizontal equation of motion. We'll talk about the different scales of horizontal motion. And then we'll start looking at the equations of motion in the vertical. And specifically, we'll look at the vertical forces that play a role in moving around air parcels. And those will be the pressure gradient force, the Coriolis force, the advection, the turbulent drag, which we've all seen before. And in the vertical, we'll add in gravity. So here we have, once again, our horizontal equation of motion, which you should recognize by now as being the sum of all of the accelerations from the relevant forces. And the scales of horizontal motion range from the turbulent scale, which is way down into the millimeter, centimeter range, all the way up to global circulation, which is on the scale of 10,000 kilometers. And what we discovered is that depending upon the scale of the motion, it has a certain time scale associated with it, in that the larger the scale of the horizontal motion, the longer the time scale that's associated with it. So, for example, turbulence, whether it be the turbulence cascade or turbulence production, has time scales on the order of less than 1/10 of an hour. And the thermals and the tornadoes are generally also less than an hour. By the time you get to thunderstorms, which have a horizontal scale of 10 kilometers or 10 to 100 kilometers, they have time scales between an hour and a day. Hurricanes and mesoscale convective systems, which have larger horizontal scales, have commensurately longer time scale as well, etc., etc. And we have names for some of these horizontal scales, and the ones that are going to be most commonly used are the macro scale, the mesoscale, and the micro scale. So macro is basically reserved for planetary scale and synoptic scale. So these are the largest scale items. The planetary scale are on the order of 10,000 kilometers, and the synoptic scale would be our typical weather fronts, which have scales of a few thousand kilometers and time scales of a few days to a week. The mesoscale is everything that falls in between that and the micro scale. So mesoscale are things that are between about 3 kilometers and 700 kilometers. This would involve all of your thermals, your thunderstorms, your MCSs, mesoscale convective systems, all gust fronts, all of those sorts of things fall into the mesoscale. And then in the microscale, this is where we have our boundary layer turbulence and our surface layer turbulence. So basically all the turbulent cascade is essentially moving down into the microscale. So now we have the vertical equation of motion, and it looks very similar to the horizontal equation of motion, except that we have removed the centrifugal force and we have added gravity. So let's look at these forces or these accelerations in the different directions. So here we have the acceleration of due to the pressure gradient force, and it's going to be equal to -1 over the density times the pressure gradient delta P over Z. And this is in the k-hat direction, which is in the vertical direction, which is the local upward direction. The Coriolis acceleration. This one is the acceleration due to the Coriolis force is equal to 2 times omega, which is the rotation rate, angular rotation rate of the Earth, times cosine phi, where phi is the latitude, and times u. So there is a component of the Coriolis acceleration, which is in the vertical, that arises from wind in the east-west direction. So here we have the vertical advection acceleration equation, where the vertical advection of momentum is equal to -u times the gradient of the vertical wind in the east-west direction, delta x, minus v times the vertical gradient, the gradient of the vertical wind in the north-south direction minus the vertical wind times the gradient of the vertical wind in the vertical direction. And this is in the k-hat direction. And then we have our turbulent drag, which looks very similar to the turbulent drag in the horizontal. We have our term Wt, which depends upon the stability of the atmosphere. And then we have the vertical wind speed W over Zi. And just to clarify, Zi is the height of the boundary layer and not the roughness length that I referred to in the previous lecture. And then we have gravity. Now, we've already seen that gravity changes with height. And we've seen the G of Z equation, which is equal to G naught times the radius of the Earth divided by the radius plus the elevation above the Earth's surface squared. So we know that gravity gets weaker with height. What we haven't talked about yet is the fact that gravity also is a function of latitude. And the reason being is that as the Earth is spinning, it provides us with a centrifugal force, and that centrifugal force depends upon where you're at on the planet. So the largest centrifugal force is at the equator, where the Earth is spinning the fastest, and it goes to 0 at the pole. So what we've decided to do is to take that outward directed centrifugal force and that which is in the vertical direction locally, we'll just simply add it to gravity and define G naught as the effective gravity. So G naught is going to be equal to our Newtonian gravity, G star, plus this the centrifugal force, omega squared cosine phi times the radius of the Earth, where the radius of the Earth is 6.367 times 10 to the 6th, and omega is the angular rotation rate of our planet, which is 7.272 times 10 to the minus 5th radians per second. If we put together the first order terms in the vertical equation of motion, we'll find that the dominant terms are gravity and the vertical pressure gradient force, and that these are the dominant terms by several orders of magnitude. And you've seen this balance before in that it looks very similar and should look exactly like the hydrostatic equation that we had very early on in the semester. So we have minus 1 over the density times the delta P over delta Z is equal to gravity. And in a hydrostatic atmosphere, there is no vertical motion because these forces are balanced with one another.